All right, hello and welcome everybody to episode 9 of Evans Imagines. I'm going to get this done before the end of this holiday season. While I still have this rant all good and canned for you. So this particular lesson we'll be talking about is the jerk of the universe. There's a couple more items, obviously, from last time's cutting edge list to do. We have the exploration of a reduced mass of positronium and muonium, the mass of virtual pairs, and then the prediction of negative jerk. So jerk or jolt, just for anybody who hasn't been here for the last ones / doesn't remember, is the derivative of the acceleration. So you probably remember very much from your physics classes growing up. You had a lot of comments about, what was it? The derivative velocity being the derivative of the position changing in time, the acceleration being the derivative of velocity changing in time, and the jerk is the derivative of the acceleration changing in time. So obviously you consider the jerk when you're talking about the biggest forces, etc. But let's get right into it. I'll get a screen share up. You guys have seen my beautiful face and a little extra for the holidays. Okay. Boop. So this is what I was talking about. Let's get it slideshow form just so I can see it as well as you guys can. Yeah, so first, this has been a homework problem off and on various times throughout. We're going to talk about the reduced mass of positronium and muonium because there's a good experiment being done here. We've talked about it a few times and a couple different ideations, versions of it. The idea is positronium, muonium, these are bound states of one positive mass thing, one negative mass thing. Now, it's not the same as when you have the strong force holding them together, like in a meson, right? It's a little further apart, so the force is not going to be as strong between them, but nonetheless, even though they're further apart from each other, so they're not pushing as hard, they're each feeling an opposite force from the Earth, right? So we have to think about which thing they're feeling when. Now, notably, I'm not the guy who invented this. There's the muonium anti-gravity experiment, person putting his entire professional reputation on the line. So go look up Professor Daniel Kaplan. This is his thing and a couple of other people in Illinois. But as you've seen in our discussion of this sort of topic, we have seen that the inertial mass being the absolute value or magnitude of the gravitational mass allows us to consider these special situations. Meson's kind of relevant. Of course, if they lasted a longer time, we would talk about their weight rather than their CP violation. But we're really looking with mesons into what happens with their decay because they decay really fast. So yeah, this is popping up straight from, you don't have to get too controversial. Just go to Wikipedia, look up the reduced mass, and you would have had the answer to my occasional trick question about what is the inertial mass? What is the mass of these things? So the reduced mass is the effective inertial mass appearing in the two-body problem. It's the quantity which lets you reduce the two-body problem to a one-body problem, important for these bodies. However, the mass determining the gravitational force is not the reduced mass. It is the total mass. So the reduced mass, fine. That's inertial masses. We're adding them together with the absolute value signs in there. But the gravitational force, you are adding in there with the sum of the bare masses. So if it's a negative adding to a positive, the gravitational force we would expect from the resulting item under any sort of field is 0, because if it's mass, then it have half push, half pull, and if it's an anti-mass, then it have half pull, half push. Right? So those in the opposite order, hopefully. But yeah, so that's the breakdown of this idea. It's not a particularly complicated one. So the reduced mass is the inertial mass. So we expect positive vibrational frequency to these unusual bound states, which doesn't seem like a problem to you guys because I'm presenting it like I just invented all this stuff. But yeah, I thought about this for quite a while and was pretty worried about it because initially I thought, well, wait a second. So if you look at the formula for reduced mass, it's M1, M2 over M1 plus M2. M1 plus M2 in the denominator there. So if you don't remember that those are inertial masses and thus get the absolute value sign, you have a big problem because you would have M1 plus M2 or M1 times M2 in the numerator, a number divided by 0, right? Don't like having not a number in there for my masses. I like to have masses that are numbers, not not numbers. So anyway, also because we've actually observed these, you can go and do infrared probes of whatever little bits of hydrogen, anti-hydrogen we can make. And we know well, and not just anti-hydrogen, the mesons, all of these things. Sorry, it has to be a balanced state to have a vibrational frequency. But muonium, positronium, we can see the vibrational states of them. They have them. They are non-zero. They are numbers, not a numbers. So this was an important point for me to get through. That's why I've left it in the lectures. Maybe you are thinking about it too, but it's a mistake. We remain uncertain, however, like I was saying, maybe not even uncertain. Wikipedia seems to think it's obvious. I seem to think it's obvious what their interaction would be with the Earth. It's possible that muonium and gravitonium, if you could make them, gravitonium, positronium, any of these thing and their antiparticles, they form a bound state because you have a positive and a negative, and the positive and negative charge attract, but the positive and the negative mass cancel out. So you have these two weird effects. And yeah, I really like Professor Kaplan. You've heard me talk about him a lot on these lectures. I think he's the coolest American. Ulrich doing a lot of good work too in Iowa, but he's recently proposed to use some of FermiLab, not just to try to build tabletop experiments with these, to get more of the thing he needs to have some certainty about the whether or not the gravitational mass of muonium or positronium is zero. Excuse me. Take a drink. Okay. So yes, there's a proposal to do this. We'll find out. It's a cool test of our theory, right? Because if we think that antimatter has the opposite mass of matter, maybe you can find it this way before you can even produce enough antimatter experiments. Like I was saying, I've been trying to make a grand bet with somebody about whether or not the CERN experiments will go up or down in terms of the antimatter. Will it fly up or will it fall down? And they're just not making that much of it. So I'm not sure they're going to give me they're not going to give me the certainty that I want. Whereas muonium, positronium, these are lasting a lot longer. You can make a lot more of them. They don't immediately annihilate. They're bound to each other. So, I mean, they annihilate eventually. But I think that these are a possible alternative verification, or it's a crucial experiment, right? And the problem is, we already have 97% wrong, 95.6, whatever it is currently, from the cosmological study, which was the cosmic microwave background anisotropy. I forget the fancy WMAP. That's the word you're supposed to say quickly to people. But so yeah, that's 97% or 6% wrong. And this is just 100% wrong, right? If we thought the standard theory should have whatever regular reduced mass, now it would be zero, but that's not negative, right? So even though it could happen first, it's not quite as convincing of a crucial experiment. It's 100% wrong. That's bad, but we're already at 96% wrong and people are just patching it, right? So if people are willing to patch 96% wrong knowledge, then they're probably willing to patch 100%. I just hope 200% is like a bridge too far. I don't know if it is. Yeah, I think these are promising experiments. Depends on whether energy or curvature in energy space is the more fundamental thing or something else. Oh, right. This is bringing in other people's theories. So yeah, apparently I didn't finish this thought, but yeah, so I've had some conversations with McGovern over the last couple of weeks that have been interesting. That bit string physics front, it's not really part of this, but it is interesting that problem of antimatter containment is apparently making some leaps and bounds. I hadn't heard about this, but the CERN experiments, they're now trying to do a tabletop outside of CERN antimatter producer or something like that. I mean, come on, they're having trouble doing it at CERN. So maybe they do it better in a van or whatever it is. But this is just like, there were cute movies about driving around with an EMP in your van and stuff in the 90s. And it strikes me as probably, ridiculous as this is. So hopefully they're able to do it in 20 years, bring antimatter, well, hopefully. So yeah, there's a little bit of a problem if you have a lot of antimatter from a defense standpoint, in that it's way, 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 way better than uranium, whatever enriched form people use to make nukes. Number one, hard to make it enriched. Number two, when you do make a nuke or whatever, you're eliminating a neutron or a couple of protons or whatever. And when you do an antimatter explosion, you're eliminating all of it, all of the antihydrogen. So, right, I mean, there's more. You got the proton, you got the anti-electron, you got the anti-neutrons. It's a lot more energy per gram. It's a lot more energy per whatever mole, you know. So I worry about antimatter containment and antimatter defense. I've also found out that Pierre Noyes had started at SLAC, he had started a working group to prevent the creation of antimatter weapons. So, you know, if you do take yourself seriously, that's what we really need to think about next, right? Like before we have the Manhattan Project of antimatter nuclear bombs, we should probably recognize that there is no useful application of antimatter bombs on Earth. It's bad. The application of antimatter bombs is the Death Star. So if you want to be Darth Vader, then you can build, or I'm sorry, I don't know my Star Wars lore well enough. You can all tell me whichever guy it was. Somebody in the Empire was building the Death Star, and you know, it's the bad guys. So, and they do it to destroy whole planets that they don't like. So until we get another one, this is worse than a nuke. Like one nuke mistake, okay, might wipe off. We count on mutually assured destruction because one nuke is not going to blow up the Earth, right? Even our biggest nukes deployed at the best spots, not going to blow up the Earth. On antimatter bomb, blow up the Earth. Like not hard to make it. You make the same conventional size bomb and you will blow up the Earth. So a little bit of a problem. Also, I mean, so I've done a whole thing on this. Maybe I'll make it a separate one of these points. It's not on my list, so I don't think I have. Yeah, I don't have 7, 9, 10. None of these things are the, what's it called, Death Star. But I did do some calculations on the Death Star at one point because you have to calculate as you make the big antimatter bomb, it has the opposite of escape velocity, right? Like as you have to have a force velocity to push it down. So you have, can you create an antimatter bomb that while in geosynchronous orbit will make it to the surface of the Earth or any planet to destroy it? And the answer is basically yes, but it will also probably destroy the Death Star. So disposable Death Star, maybe not the best idea for building a huge Death Star that only works once. But that's probably why I left this as it was. Oh yeah, I have virtual pairs as a separate point. Yeah, good. It's kind of a separate point. So I bring this up because Feynman, Weinberg, everybody, like if you really, really take yourself seriously about quantum field theory, you are always worried about virtual pairs. And if you are always worried about virtual pairs, then you are worried about me telling you that that you're worried about their mass. So I'm not worried about them. You know, number one, I'm not that good at quantum field theory. I don't really care about them. I've never seen them like pop out and be super important. But also, virtual pairs have the word pairs in them. What are they a pair of? They're a pair of two things with equal and opposite energy. Mass. let's say that for now. Equal and opposite everything. Really. They're a particle and its antiparticle. That's what's coming out in some combination. You know, eventually they turn into a bunch of other stuff. As I understand it, it's possibly wrong. Send me an email at boney@alum.mit.edu if this sounds like it's nonsense and you know it's nonsense. But I don't think it's nonsense. And the answer is just simple, right? Like we've already talked about. Yeah, okay, the inertial mass of a virtual pair, should it become real, and it needs to do accelerations and you need to do some math on it, you can do the math like it's a regular particle with the absolute value sign around its gravitational mass. But its gravitational mass remains zero. It's different from its inertial mass because it's not a relative motion thing. You're not causing stuff to move. It's in the context of whatever's around it. That's when you have the zero, because in the context of everything around it, you have a local asymmetry of matter. And that local asymmetry of matter, one way or the other, is driving pretty much everything from, yeah, all of your local observations, like you call yourself matter. There's the interesting point Feynman went on for a while that I went and read recently about like the left-handed universe, or he called it something weird. But basically the idea being that if you were talking to somebody sufficiently far away, talking to with some sort of crazy device that's not specified, but you would have no ability to tell via either one of you could not communicate the fundamental parts of your knowledge, because you couldn't, for instance, like because of light signatures and stuff, tell like is what we're calling matter what they're calling matter? Don't know. People have tried to make CP violation directionality like the common basis for understanding, which if we talk to people far away, we'd be like, oh yeah, well, sure, your CP violation is in the same direction, right? Yeah, you got a lot of assumptions in there, guys. I don't think we can tell that apart. But to me, yeah, you don't have any gravitational mass to a virtual pair, and the proof is in the CP violation. It was predicted, it was found. What? Man, yeah, you've heard me go on this rant before. ML good. I love you. I should probably, yeah, write something up about a retrospective on ML good at some point because did not get enough respect. It gets no respect. Okay. Yeah. So each virtual pair is just a non-bound state. So they come out, has the same characteristics otherwise. So that's I guess that's the one counterpoint you could make here is that like a virtual pair is not necessarily immediately recombining. And in the case that it does not recombine, then eventually the stuff gets far enough apart where each you no longer have them behaving like they have a center of mass behavior, right? Whether it's up or down or a net mass behavior. You have the whole net mass becomes a lot bigger because there's stuff in between. Oh yeah, and then this is something I just hadn't realized. This is probably why quantum mechanics like bothers Einstein and a bunch of other people, but has never bothered me before until now. Conservation of momentum, conservation of energy. These are super important concepts that imply an exact answer, an exact energy, an exact momentum. But we do not know that energy or momentum, right? We have uncertainty about those things. But we are reasoning from their being conserved exactly beyond uncertainty. So, you know, I think that's interesting. And I think what's happening here is the words that we have are insufficient. The words energy, the words momentum, that's what's happening when we have language like this, where we are both implying the importance of knowing the total of something and saying you can't know it, right? I've tried a couple of other options. This is all very speculative, as if my entire lectures were not very speculative. But I've thought maybe we can use words like energy norm or mass norm or energy squared. Maybe that's a more fundamental quantity. Although I must say my initial calculations suggest it is not. So I think there's something else there. But all these ideas are pretty bad. Don't chase them down. Let's see. Yeah, I think there's, though, when we do go down, like, we probably need to be talking about entropy or something else when we have concerns like this. So, because that's, you know, what it wound up being. I'm reading a lot of Planck and Boltzmann over the holidays. Okay, I'll just move on because the virtual pair thing is not a problem for me. I do not, in my theory, have them having a net gravitational mass. And as long as they're virtual, what that basically means is they're close enough to each other that there's nothing else in between that they're interacting with except when you need them there for calculation purposes, as I understand. Okay, so yeah, if you learn one thing from this lecture, no matter what age group or bracket or interest in science you are in, it is what the jerk, or if you're UK or whatever, jolt is. It's the derivative of the acceleration, right? And it's important to talk about the derivative of the acceleration because that's the derivative of the forces. And if you assume there's no net force in your problem or you have a constant force, then the derivative is 0. And if you have a constantly changing force, then you can make statements about that too. Generally on Earth, right, we have the constant acceleration. So when you are in the field of the Earth, the derivative of your acceleration is the derivative of the constant g, which is 0. It's a constant. So with time, and thus we don't talk about it. That's why it's not in the classes. It's not an incomplete class. Like that's really all you needed for mechanics, right? You didn't need the jolt because if you're dealing with non-uniform accelerations, generally you don't care. So as a result of not having thought about jerk, you have potentially not thought about the jerk of the universe. So welcome to this lecture, which is, I have some animations coming up. So it's actually kind of fun. It's a derivative of the acceleration. So it's kind of important, changes in force, right? I mean, like we talk about them in terms of changes in force, but as long as we're given that there's not a change in inertial mass, which not even I'm saying. I think that you have a constant inertial mass. It just can sometimes be the absolute value of your gravitational mass. So the only thing in the F equals ma thing that can be doing changes if you have df dt is the A. So we should have been talking about the ADT a little bit more, I think. I shouldn't be finding out late in my education what jerk and jolt is. But thankfully, you don't have to. You can learn it from me here. Okay, so in my theory of the universe, right, we have the over time tracks are getting further apart. So we'll run the tape backwards. I think in another lecture, it's a lot more complicated when things get back to the beginning of time because everything's hot and dense. And we have to talk about what was the attractive force that they overcame, right? Because I don't think it's tough. I mean, gravitational repulsion eventually will overcome any force of any, tiny, whatever it was probably a 1/r to the 6th or 1/r to the 8th or something, lead order force in the early universe, or more complicated than that, who knows? It was eventually overwhelmed, right? And eventually, in my theory, it's overwhelmed in every direction, and you have equally likely matter going one way, antimatter, matter, antimatter. It's like a patchwork universe. So that's why it's important to push back on those patchwork universe objections from Glasgow and yeah, that group back then. I don't remember who else was on that particular paper at this time. But the basic point is to get it going everywhere. And so let's simplify it to a binary universe for now, despite the fact that that's ridiculous. And I will let you trust me that the application continues to work, whether or not it's a binary universe. Okay, so so you have your part of the universe that no matter where you are, you know that there's a part of the universe where you're pretty confident in stuff. That's the part you've flown spaceships around. And there's the part out there. And if you're assuming everything came from nothing, then the part out there has the equal and opposite net gravitational mass to the part in here, so that the overall gravitational mass of the everything is nothing. Okay, so I think that's all pretty clear at least. But that also means that if you think about here, and let's just now approximate there as everywhere else is also here. So it's like in a line. Then they're tracing out kind of the opposite of, it's not Coulomb potential, the gravitational potential, right? I mean, like gravitationally, you are pulled to the Earth when you're really close to it, and you're pushed from the anti-Earth more when you're really close to it. So you're pushed, when we were these little proto tracks of galaxies, when we used to be close, we were pushed really fast. And now we're pushed a little slower. So there's a couple of things here. Number one, a cute little animation. So right now, they're moving us up, the speed at which they're going is faster than ever, right? But the acceleration is diminishing. In the past, it was greater. Now it is less. Number one, that's an explanation for, students paying attention / do you have a lot of cosmology knowledge? That's hyperinflation. We have a natural hyperinflation in our theory that doesn't exist in the current theory. Current theory has Guth patching up with bread and stuff and the space-time, and I don't like it. But ours just appears from gravity. It appears from stuff getting further apart on average, and you have the 1 over the average distance. And as the average distance gets bigger, that number goes down. And so your acceleration goes down. Now, it is still accelerating, right? That's an important fact. Everything, we've got the Hubble observation, right? That is, the further you get away, the faster the stuff is moving away. And that makes sense too. All this adds up. So I like all the cosmological data seems to fall pretty nicely in line. Not just the dark energy, not just the dark matter, hyperinflation, and So I didn't even make a slide for explaining hyperinflation. So that tells you how much I care about that. But I like running it back to the Big Bang, right? Because that's more fun. Everything's a lot closer together. What was the stronger force then? Yeah, I guess that's the only point I was making at this point. Let me go back here for a second. So the other point is, so it used to be higher. When it was closer, you had a 1 over r, where the r was smaller, so the force is higher, so the acceleration is faster. That's why you had hyperinflation. Then you get to now, where everything is just like it is observed. Stuff's pretty far away. The acceleration is slowly changing, very slowly relative to the entirety of human existence, right? And that's a weird little time frame. Nobody's ever really had a theory that is valid for where all of human existence is considered a tiniest part of a curve And so it's constant. It's not really constant, it's slightly changing. So that's kind of, we got a lot of people on this tip in terms of it's modified, Newtonian, whatever. People are modifying gravity already to make it fit like this is, like it's changing over time. But you don't need to change gravity. Let's keep our constants constant. Like, let's also explain where they came from. That's bit string physics. I got a little earworm for it. Maybe I'll make a series on that someday. But aside from we need to explain the constants, they're constant until you have a reason they're not constant. And so I don't like just playground stuff. This is not playground stuff. This is, we're observing dark energy. We're observing dark matter. And we don't need to play around with our constants. We need to play around with more important stuff than that. So, okay, backing up. So now we're at our part of the universe. What's the future like? Because the next slide is going back to the past, and we can talk about that at length. But the future is stuff gets further apart. The average distance between everything continues to increase. We have this 1 over whatever term with our average value between tracks getting bigger and bigger. So what's happening to the acceleration? It's going to 0. So the jerk of the universe, number 1, is negative. It's going down. Number 2, it's going to 0. Now it's not going to get there ever, right? In this theory, there's no opposing force. The biggest thing, because it's also the weakest force, the largest, gravity has a push over the longest ranges that is unopposed by anything in this model. So that's why I say the jerk of the universe is negative, and that's why I say the acceleration of the universe tends to 0 over time. So the jerk of the universe is negative. Now, I think that's pretty good as like titles to books go, but it's also very tangential to the main point of antimatter falls up, right? So probably a little bit better to center your book around antimatter falling up, which is a very relatable concept, than to center it around the jerk of the universe, even though that's a cute turn of phrase. So then we've talked about going out, and I've kind of hand waved that we might want to go back. So when we go back, we do immediately recover hyperinflation. That's good. But we also can potentially go back past the bang, right? If we are saying gravity is what was driving everything apart, then we can look at when it was held together. So first of all, if gravity is what is driving things apart and not electromagnetism, it must be the case that a large tract is very tiny charge. And I think that matches out like with my general sense of how the world works. I'm not sure if it's strictly true. We would need the average number of charge, like the average percent charge of a galaxy or whatever would have to be below whatever the ratio of the electromagnetic constants to the gravitational constants are, right? Because otherwise they have the same with our curvature. So if something is charged with a charge of 1 and it has a mass of 1 in the same units, which is a ridiculous unit set to choose, but it would be, you've heard that electromagnetism is much, much stronger than gravity. And that's true for charged particles. Now, first of all, I just learned over this break. Do you guys know how recent charged particles are as a concept? This is wild to me. Like, it is 2022. Happy New Year, everybody. But charged particles have only been around since 1910 or so. 1910. The guys who invented like all of electromagnetism did so like thinking those were not real entities, that you couldn't have electrons. So anyway, just wild to me that Millikan oil drop experiment wasn't just establishing the charge of an electron. We were establishing electrons really recently. Like you feel strong about it because you learned about orbitals and stuff of electrons within 10, 20 years, but we didn't even know that not just electrons, ions, like that there were particles that were charged and could be approximated as points. That's really a recent concept. I gotta think more about that concept if that's so recent. But okay, my main point is if we go way back and dial it back, and we have these tracks getting closer and closer that are proto uncharged. So they've got like one part in 10,000, 20,000, 100,000. I probably should have done the math before I started the lecture. Whatever it is you need, a very tiny percent are charged particles. And so that means you have your positively charged and your anti-charged, like you still have a 0 net charge in the universe, right? So that's how you can do the math on that, just like we're doing with the gravity. But the difference is that those clumps cannot get together, or like let's see how to put this. If you had a net charge, the charge, because of the spin of the photon, would, like charges, repel, opposites attract. I think I've got that right. I've talked this so much for gravity recently. And so since like charges repel, you wouldn't have these clumps. The reason you have the clumps is because they're all like mass, right? And so you have the like masses together clumping. And that's why I think we can make the observation that even going back to proto times, that these clumps must have been lightly charged, because if they were heavily charged, they would have broken apart under their own charge repellation or whatever. So presumably that's what was going on. If you run the back eventually, and eventually your R across a tract gets comparable to your R between tracts, your average distance. So as they get closer and that they're no longer separate, they're like back in this, I'm associating that with the transparency horizon entirely ad hoc. I don't know, I've never done the math on whether or not you could actually have them together and still see into it. But it seems like as those R's get to be about the same, stuff's very close together. And it is probably in some crazy milieu, some weird form. We need to, we, meaning me, needs to go and figure out what my approximation is for the early universe. But my basis of it is a lot of stuff came from nothing, all there together. Tiny little sphere for starters. Why not make it all in a tiny sphere and then boom, and then it's bigger. But so tiny little sphere all together, and there's more. There's a little fun thing we can do there. So when everything is together, right? So whatever initial amount of stuff, let's say before the Big Bang, but sometime after the beginning of the universe. So at a convenient time that we can never ever look into because it's past the transparency horizon, we're never going to get any light from it. We can imagine a bunch of stuff, some amount of stuff, let's call it N stuff. And since everything came from nothing, it's approximately N and a half, or N half of N is approximately the matter, half of N is approximately the antimatter. And so when it's all really close together, the main thing that's happening is boom, 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 boom. Boom, 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 boom. Boom, 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 boom. Boom, 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 boom. Boom, 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 boom. They are exploding a lot, right? Matter and antimatter, when it comes together, boom, explosion, gamma rays. So we're going to have a lot of booming, 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 lot of booming for a long, long time relative to time not existing. So, for until we exist, that is happening. So in this little imagined volume of magic that is not specified, granted, a lot of concerns there with this magic volume. But if you look in there initially and you say, okay, I had n/2 and n/2 of matter and antimatter, and then I look back later and it's about to be the splitting apart thing that it eventually does to become us, there should have been a lot of booms, because they're all so close together and that's what they do. They like to boom. So, you define whatever collisional, what's that called? The parameter for explosions or whatever, and you see how many of them do the exploding. It'll be a lot of them. And it seems to be very consistent to me with the observation of a famous problem, which is the photon baryon ratio. So when you look at back to the beginning of time, the amount of photons that came out of the transparency horizon and the amount of stuff that came out of the transparency horizon, there is a lot more photons than there is stuff. And this is completely unmotivated in the standard model. It's just another number that people are like, whoa, crazy. And that's from a long time ago, right? So we're never going to know, gosh. But look, here it popped out, right? It popped out just of that eventually we have a repelling gravitational force overwhelming a higher order force. So unspecified here, but I have a clue. It's just not part of this lecture series. It's van der Waals force. So if you want to go have fun with it, I'm also doing plasma stuff next. So we can see if that becomes its own little thing. But for now, this is the next lecture that I have not written. Probably write it right after this. We're going to talk about the last few topics on this list of things with my negative mass lectures. The relationship between negative energy solutions and detailed balance. This is pretty interesting, like detailed balance and microscopic reversibility versus macroscopic irreversibility. I've been doing a lot of reading on this over the holidays. I don't know how many slides that's going to wind up being, but yeah. Early universe simulations. Hey, great. We are going to talk about some of my plasma physics nonsense. That'll be fun. And then number 10, you can think about what is the equivalent of wormhole-like travel. So obviously, I think that since the Einstein field equations are just an approximation, we're not going to really have Einstein-Rosen bridges or whatever the equivalent thing is, because those things are a product of a space-time that is non-existent. It's just an approximation locally. So don't try to travel through an approximate wormhole. You know what I mean? You want to travel really between galaxies. Well, that's also, I'm not sure you can't, you may not have to provide all of the acceleration. Now, that's not to say you're traveling through some crazy wormhole, but it's wormhole-like, right? The idea that you're going to go faster than you could with just your own propulsion. So kind of dwell on these for a little bit. Number 7 in particular, see if you get anywhere thinking about the relationship between the negative energy solutions to the Dirac equation and detailed balance, because that's something I think it's right. I think that's going to be my next paper on this topic, just to put a little preprint out there, because it's pretty important that people recognize detailed balance is a real thing, and it should be there in all of your equations. And if it's not there, well, I guess that's the reason why it might not be my next paper. I did see the Pettit group did a great paper on this. So go check out, for next time, look up Natalie DeBerg, DeBergh, I think. She did a great, so look up detailed balance, or sorry, time reversibility of the Dirac equations. Yeah, she did it right. I was looking it up to be like preparing this next little preprint I was about to talk about. And then I remembered why I'm not doing that preprint so fast. It's because Natalie did it right. And the Pettit lab is doing a lot of things right. So like I say, they are also the first people without dark matter or dark energy. So they got to one of my little goals before me. So yeah, I'm not steamed though, as I've mentioned. When we're out here in revolution land, we need everybody to be friends. Like, not just because we don't want anybody to go Boltzmann or whatever, pick your favorite crazy scientist who got really sad for, regular reasons as being people. Boltzmann, Majorana, some people who've just disappeared or killed themselves or whatever. But because there's really good work they're doing. I mean, I'm still not comfortable with biometric gravity, but I see what they're doing and it's really good. And so, I may disagree with them here and there, but the main thrust of everything I'm saying to all of you guys who are doing, however tangentially related to this work, is keep doing it. Like, you're not going to get any support from reviewers. You're not going to get any support from grant agencies, but you're doing this is important work. This is the right answer to the universe. So congratulations. It's just that it's not very profitable to, just like finding a cure for cancer. That's why I'm not using my chemistry degree to go work in pharmaceuticals, is because it was very clear early on, there's no mechanism to cure cancer in a pharmaceutical company. If you cure cancer, then let's say that your major drug is being sold to cancer patients and you just cured it. That's ending your company, right? I mean, there's just no, capitalism and curing cancer are not compatible. So as long as we have capitalism, we will have cancer. And as long as we have physicists who need grants, we will probably have a lot of dark energy that we just can't quite get to, right? Because I mean, if they explained it, physics gets very boring. That's another lecture I haven't been able to find that I remember reading from Feynman, where he talks about like what happens after we solve physics, right? Because I mean, he had just, at the time, he was feeling pretty happy about, unification. And what do we do once, 96% wrong becomes 100% right? It's just like details, and it's like minutia instead of really fun big problems about the universe, right? So I don't know, I probably wouldn't get that into it if it wasn't 100% wrong. I'd go look at something else that's 100% wrong. Like they have dark genetic matter, right? Oh, I wonder, is that really there too? I bet it is, right? No, that's also not there. We're going to have a series on that for sure. I'm a Lamarck guy in addition to being a Kuhn guy. So not a Lamarck was right guy, but a Lamarck was righter than he is traditionally reckoned guy. Because yeah, giraffes don't reach for apples with their necks, but you know who does reach for apples with their hands is people. And so if you think that our agriculture is not affected by our history of agriculture, okay, you're just nuts. So anyway, we'll get into that next lecture series. Next time we'll go over this stuff. And thank you for watching. Oh yeah, let me stop sharing so that you can see my beautiful face a little bit more in detail. As I say, goodbye, and I'll see you next time on Evans Imagines.